Uh, Students, today we will learn about the Gibbs phase rule. Uh, so this actually gives the number of parameters that can be varied independently while the number of phases in equilibrium is preserved. Okay, it's basically a relation between variance or number of degrees of freedom, a number of components, and the number of phases at equilibrium for a system of any composition. The F stands for degrees of freedom or variance. This is a number of intensive variables that can be changed independently without disturbing the number of phases in equilibrium. For example, if we have ice and water in equilibrium, okay, so if you change the pressure for that equilibrium, you have to change the temperature in order to maintain that equilibrium, right? Otherwise, that equilibrium will be cannot be maintained. What's a constituent? Constituent of a system is any chemical species that is present. For example, let's take a mixture of ethanol and water. That's a single phase because ethanol is completely miscible with water. But it has got two constituents. One is ethanol, another is water. Let's look at sodium chloride in water. It ionizes and produces sodium plus ion and chloride ions, and of course there is water. So this is a three constituent system, but it has only two components, because if I know how much of sodium plus is in the system, automatically I know how much of chloride minus in the system, because electron neutrality requires the number of sodium plus ions to be equal to number of chloride ions. So we need to, it's basically a two component system. Okay, so now go back. See, what is component? It's a chemically independent constituent of a system. That's a component, right? Because if we know sodium plus, I know how many chloride is there. So they are dependent on each other. So any one that I should know, that's enough to understand the system. Okay. So let us now understand the phase rule with a one component system, because in our syllabus we have only one component system. Assume that the C, that's a component, is 1 and there is one phase in that system. Say for example liquid water. Okay, so that's only water, pure water. There's only one component and the phase is only one phase because you are taking the liquid water. In this case I can vary a pressure such that still I retain the water, or I can vary temperature such that still I can retain water. So independently I can vary pressure and temperature. So I have got a 2 degrees of freedom. Okay, either I can vary pressure or temperature, still I can maintain the water in liquid phase. Okay, so F is equal to 2 when C is 1 and P is 1. Suppose in the same one component system, if I choose to have two phases in equilibrium, for example, that means there is an alpha phase and beta phase like ice and water. Okay, so if they are in equilibrium, we know the chemical potential of alpha phase must be equal to the chemical potential of beta phase at equilibrium. Okay, so in this case if I change the pressure, I must change temperature in order to maintain that equilibrium. Otherwise you will have either ice or liquid water, right? So the number of degrees of freedom is 1. Okay, I can't independently change both pressure and temperature. If I change the pressure, I had to change temperature such that the equilibrium is maintained. So suppose if I have three phases in equilibrium in that one component system, so that means alpha in equilibrium with beta, beta is in equilibrium with gamma, like ice, water and water vapor, right? That means alpha is in equilibrium with beta and beta in equilibrium with gamma. This gives two equations. Okay, the chemical potential of alpha phase is equal to the beta phase. Similarly, the chemical potential of beta phase is equal to the gamma phase. Okay, there are two variables, pressure and temperature for this. Okay, so I have two equations with two unknowns, pressure and temperature. So there will be only single solution, because this is like equation with the two variables, x plus y, some number, and again another equation, say 3x plus 4y equals some number. If there is a solution for this, that should be a very specific solution. There will be one particular x and y. Okay, that will be the solution of that. So similarly here there are two variables, pressure and temperature, and we have two equations. That means there are two unknowns. Okay, so there must be a single solution for this. Okay, Therefore, the number of degrees of freedom is 0, because if I disturb either pressure or temperature, I will lose this equilibrium of three phases. Okay, there's only one choice. There is only one point which denotes which represent one particular pressure and temperature, and that condition you will have all the three phases in equilibrium. Okay, so suppose if I have one component system with four phases like alpha, beta in equilibrium, beta in equilibrium with gamma, gamma in equilibrium with delta. In this case, just like here, when you have three phases, you got two equations, okay, with the two unknowns. Here you will get three equations with the two unknowns. Okay, so no values of pressure and temperature will satisfy all the three equations, and hence there is no solution for this problem. Okay, in summary, for one component system, if I have a single phase, then there is a 2 degrees of freedom. If I have two phases in equilibrium, then there is 1 degree of freedom. If I have three phases in equilibrium, I have no degrees of freedom. If you generalize this argument to a C component system, like sodium chloride in water, okay, then I need to specify C minus 1 mole fractions, okay, which are independent, right? So you can follow this calculation here, then finally you arrive at a relation which we called as a Gibbs phase rule, where number of degrees of freedom F is nothing but the C minus P plus 2. That 2 is temperature and pressure, two variables. Okay. Now let's look at the phase diagram of carbon dioxide. So generally the phase diagram will look like this. So I have given the finer details of this carbon dioxide phase diagram here. So this is a temperature axis and this is a pressure axis. So TB represents the boiling point of you know this is this is the TB is a temperature at which the solid carbon dioxide goes to vapor phase directly, and this is called a triple point. So this corresponds to 216.8 right, temperature, Kelvin temperature, and pressure of 5.11. So at this point, okay, so before getting into this point, let me explain this little briefly. This area which is enclosed between these two lines, okay, wherein the solid CO2 is stable, and this area which is here wherein the liquid CO2 is stable, and in this area you have the gaseous CO2 is stable. So as you can see, this is a point that is here, the same I have shown it here. It's called triple point, where you would see actually all the three phases, solid, liquid and vapor phase together. Okay, so now let us look at the slope of the line that is separating the solid phase from the liquid phase. Okay, so that slope is a positive slope that indicates, okay, the melting point of solid CO2 rises as the pressure is increased. Okay, you can see. So when I increase the pressure this way, the temperature at which the solid will become liquid is going to increase. So that's the melting point increases with the pressure. And if you see the triple point which I mentioned, wherein three phases coexist, that lies above 1 atmospheric pressure. So what it means, the liquid cannot exist at normal atmospheric pressures, whatever may be the temperature. Therefore, the solid that is here will sublime directly to vapor phase if you left the the solid CO2 in our atmosphere. So the solid CO2 is called dry ice, because when that ice disappear, it will not leave any liquid, so it directly goes to gaseous phase. So it's a dry ice. Okay, it doesn't wet anything, right? That's why it's called dry ice. So if you want to obtain a liquid, so that means we need to apply a minimum of 5.11 atmospheric pressure or anything above that. Then there is a possibility at certain temperature you might get a liquid CO2. For example, at 5.11 and at this temperature you will have all the three phases coexisting. If you increase slightly more pressure, above 5.11, you will get only the liquid CO2, or you can go to any other higher pressure but maintain the corresponding temperature such that you have only liquid CO2. So the cylinders of carbon dioxide contain either the liquid or compressed gas at 25 degree centigrade. Okay, so this temperature here is roughly 25 degree centigrade. Okay, that implies a vapor pressure of 67 atmosphere. If both gas and liquid are present in equilibrium. So because these lines, remember these lines which are boundary between the two phases, that means over this line, any point over this line, you will see both the phases. In this case, liquid and vapor. Okay, in this case, solid and liquid. So this is a line, and in this case, you will have vapor and solid. So that's why if you choose 25 degree centigrade, okay, and apply a 67 atmospheric pressure, you would see both liquid and gaseous carbon dioxide present in equilibrium. Okay, the cylinders that we use normally in the laboratory is kept at room temperature, so it's 25 degrees centigrade. But if you want to keep it in the liquid form, so you need to apply a pressure of at least 67 atmosphere within the cylinder. If I open the cylinder, suppose, and let the carbon dioxide go out, so within the cylinder that a pressure is about 67 atmospheres, and I am letting it go out, that means it will enter a environment where the pressure is 1 atmosphere. And since I am letting it through the orifice because of the Joule-Thomson effect, there will be a temperature drop. Then you would see when the gas comes out of the cylinder, it will come out like a ice, like a snow, like precipitate, because you are entering, the temperature is falling down due to Joule-Thomson effect, and also the pressure is 1 atmospheres. At this condition of pressure and the temperature of 25 degrees C, you will not see the liquid carbon dioxide. So directly from vapor to it will enter the solid phase. That's why when you open the cylinder of high pressure cylinder of carbon dioxide into our atmosphere, you would see a dry ice that is forming. Hope this video was helpful. In the next video, I will talk about the phase diagram of water.